where it can undergo another interaction. And this process tends to happen again and again until one of two things actually happens. Sorry, Dan, did you need to say something?
No, go on, sorry.
Okay. So at every point during this encounter, it's the fate of this binary is really a competition between two different timescales. On the one hand, you have the gravitational wave merger timescale, which is the typical time it would take gravitational waves to cause this binary to inspiral. And there's the timescale between successive encounters between the binary and other black holes and stars in the cluster, what we call the binary single encounter timescale. Now, if the gravitational wave merger time is significantly less than the binary single encounter timescale, typically speaking, your binary will decouple dynamically from the cluster, where it'll merge at some point in the near future. On the other hand, if the gravitational wave merger timescale is much longer than the typical timescale between successive encounters, this process will continue until essentially one of these recoils has a fast enough speed to completely eject the binary from the cluster. Now, as you can imagine, the number of times this process needs to occur depends on the escape speed of the cluster. And so for more massive clusters, you'll typically have more interactions before the binary either merges in the cluster or is ejected from the cluster. So it's the escape speed that actually determines either the typical separation at ejection of the ejected binaries, or the fraction of mergers that occur inside the cluster versus outside the cluster. Now, if I focus just on the binary black holes that merge outside of the cluster, it turns out because of that nice bit of physics, you can actually show that the typical semi-major axes of a binary upon ejection, and therefore the typical in-spiral times, the delay time between binary being ejected from the cluster and merging later on, is almost exclusively a function of the escape speed of the cluster. So right now I'm just showing the typical semi-major axes on the top left and the in-spiral times on the top right for a relatively low mass cluster at the lower mass end of the globular cluster mass function. As I consider clusters of higher masses though, that curve and semi-major axis shifts to the left towards smaller semi-major axes. And at the same time, the distribution of in-spiral times decreases as well. And by the time I'm sampling sort of the peak of the globular cluster mass function, the majority of black holes will merge within the age of the universe, and they're ejected from the clusters with relatively small, in this case, 0.1 or 0.2 AU, semi-major axes. And so the nice thing about this is that even though this is a very complicated, chaotic process, it's entirely determined by the statistical physics of binary ejection from the cluster. There are no dials of free parameters, and it all depends entirely on well understood gravitational physics. Now, this is the story I've sort of been hawking for years, and I still stand by the fact that the gravitational physics side of this is extremely well understood. It's complicated, but it follows very well understood physical processes that can be well approximated using either direct in-body techniques or, as I'm going to show in a second, Fokker-Planck-based Monte Carlo techniques. The problem comes from the initial conditions themselves, and I'm going to revisit those later on in the talk. So when it comes to modeling these dense star clusters, there's typically a couple of different ways that people approach this problem. The most obvious is, of course, you start off with a series of particles in a box. You brute force compute the force between every particle and every other particle, and you sum the forces every single time step. Naturally, this process goes as n squared because you have to compute and sum the force of every particle and every other particle. And this is one of the oldest computational tricks in the book for actually computing the motion of particles. Anytime I talk about this, I like to show what I'm pretty certain is the first in-body calculation of a stellar dynamical system. This is from Holmberg in 1941. And what they're actually showing is the collision of two galaxies set up with a certain rotation and a certain incoming orbital angular momentum, incoming angular momentum. Now, the neat thing about this is you'll notice the date is 1941, which is actually prior to the advent of even what we would classically call computers. This simulation was actually done using a series of light bulbs on top of tiny little trays on a gymnasium floor at Cambridge. And over the course of many, many months and years, these poor grad students basically had to go out there, calculate the gravitational potential, in this case given by the intensity of ambient light at every point, which also of course goes as 1 over r squared, and then over several years turn the crank forward on this grad student powered in-body simulation. It is an absurd use of a grad student lifetime. However, it did actually work. By the end of the simulation, you actually see that this grazing encounter of these two galaxies has led to the formation of spiral arms. And this is actually sort of a very interesting early point in in-body simulations of galaxies. Mercifully, we don't have to do this anymore in gymnasiums with light bulbs. We can do this using much more complicated, modern in-body computational techniques. Of course, a large part of the problem of this isn't really coding up a force summation integrator. That part is relatively straightforward. The tricky part comes in how you deal with all of the possible options that can happen during the simulation. In particular, an in-body simulation, particularly of a collisional star cluster, will tend to form very close binaries. And so as far as the star cluster is concerned, when you have a very, very rapid, very, very close binary whose distance becomes essentially 0 on the scale of the mini parsec diameter of this cluster, you suddenly have the problem that if you want to resolve all the physics of this, your time step essentially crawls to a halt. And this has been, at least for fully collisional in-body simulations with no softening or no tree-based approximations, the limiting factor. Now, over many, many years, people have continued to fine-tune these simulations. The best known of these are what are called the Arseth codes, written by Sverre Arseth out of Cambridge. And from going pretty much in the early 60s all the way up into the early 2000s, progress in this had been relatively constant. But you can see that, I mean, even by the early 2000s, people were only doing 100,000 particles in a box. More recently, people have managed to improve this somewhat. The current state of the art in terms of direct collisional bodies of star clusters actually comes from Long Wang, who's I believe currently a postdoc in Heidelberg. And what Long Wang did was put together a GPU parallelized version of the in-body series of codes that could handle large numbers of star clusters. This is from what they called the Dragon simulations. And this basically shows the evolution over 12 gig years of a star cluster with 1 million particles in it. This had long been considered a milestone in the field. And over many, many months, they were able to integrate this star cluster over its entire 12 gig year lifetime and extract the various populations and what it looked like at the present day. The problem is, this simulation took about 13 months. And so if you want to do any sort of reasonable exploration of the parameter space, you need a more approximate way to treat this problem. So going back to going back to the in-body problem and trying to think of a way to do this more efficiently, it really helps to think about a larger number of particles. So right now, for this handful of 8 particles on the screen, 9 particles, I can count, you really need an in-body simulation. There's no way to resolve sort of the statistics of a small in-body system using any sort of reasonable statistical mechanical approach. But if I start to look at larger star clusters, let's say 10 to the 4 particles or larger, you could start to use the fact that the relaxation time of the cluster, the typical time that it would take a particle's position in phase space to change by order of itself, or more specifically, the time it would take, for instance, the velocity of the particle to change by order itself in phase space, tends to be much longer than the dynamical time, or the typical orbital time scale of a particle throughout the cluster. These two timescales are, of course, related by the number of particles. So the more particles you have in your system, the longer the relaxation time is than the dynamical time. And so the time scale it takes for particles to actually change significantly in phase space and drive the statistical evolution of the cluster becomes longer than the orbital time scale the more particles you have. The nice thing about this is, if you're in a high enough in regime where the relaxation time is much longer than the typical orbital time, you can start to use the tools of statistical physics, and in particular plasma physics, to better understand this problem. So in this case, when I'm in a high-end regime, I instead dispense with the in-body picture and start to look at the orbits themselves in phase space. Now in this case, I'm going to treat this as a series of orbits, which are specified by their energy and their angular momentum, with respect to, of course, the cluster potential. And the way I can treat this is by understanding, instead of how any individual particle reacts with any other particle, I can ask the question, on a statistical basis, how do these particles diffuse through phase space? And so the way to do this is to consider just two particles on a single orbit and allow for the possibility of nearby hyperbolic encounters. Typically speaking, what drives the evolution of these stars through phase space in the cluster is weak, distant encounters, very weak flybys, with many neighboring particles in the cluster. And the way you can treat that is to actually steal a technique from plasma physics, in this case called the Fokker-Planck approximation, where you expand, you write down the phase space of your particles, you write down the conservation of this, and then you use the fact that and you basically add this term at the right-hand side, which is called the diffusion coefficients. Essentially, how often do nearby encounters cause particles to diffuse to higher energy or lower energy? If I assume, for instance, a local Maxwellian distribution for particles in the cluster, I can write down, this is from one of the appendices of Binney and Tremaine, exactly what the diffusion coefficients will look like as per unit time. In this case, you can almost think of it as Brownian motion. A particle traveling through the cluster is not going to experience any net drift in its sort of perpendicular velocity to its perpendicular direction to its velocity. It will experience, if there's a difference in the masses, a net deceleration as it travels through the cluster. That's the top line of the equation. This is actually where classical dynamical friction comes from. What it does experience is a net drift in the perpendicular and parallel velocities squared. This is the sort of diffusion that we're actually interested in for the evolution of these clusters. Now, if I want to know the typical behavior of two of these stars after one of these encounters, this is a pretty easy Newtonian problem, right? Like this, you just look up from any undergrad mechanics class. And if I instead want to say, how does this work on a statistical basis, instead of just from two nearby particles, what would the effect of many cumulative encounters be? I basically do the standard collisional approximation. I draw a cylinder around one of the particles. I multiply it by the velocity of the particle times some particular delta t. And from that, I can work out what the actual drift in the velocity squared is going to be from the effect of many cumulative encounters per delta t. This is just using those diffusion coefficients from before. And so the whole shtick of the Monte Carlo method is to combine the actual deflection of two particles with the statistical treatment of the effect of many encounters between particles to do what we call an effective encounter. Essentially, neighboring particles in the cluster experience hyperbolic encounters with their nearest neighbor, which are tuned to reproduce the statistical mechanics, the predictions of statistical mechanics for the sort of diffusion of stars through their phase space. And so in practice, what we do is we have a cluster and we sort all the particles according to radius. And then every time step, we essentially allow that diffusion of energy and angular momentum to occur between neighboring particles. This moves the particles onto new orbits, which we can then resample according to their radial velocities. This gives us new positions for the stars on their new orbits. Then all we have to do in order to take the next time step is to resort these stars into linear order so we can then do nearest order or nearest neighbor effective encounters. Now, like all good sorting algorithms, this means that the Monte Carlo is in log n limited as opposed to direct n-body, which is n squared limited. Now, the original series of these codes were actually, of this approach, was actually developed by Michel Hénon in the mid-1970s. And in that case, he was using what are called effective stars, so particles that represented many numbers of stars at the same time. More modern hardware, of course, allows us to actually treat this on a star-by-star basis. And so in addition to treating the evolution of stars, we can add in as much additional physics to this as we want. So the cluster Monte Carlo code that we use for collisional models of massive star clusters contains a bunch of additional physics that's coupled to each one of these particles. Each one of these particles has a realistic radius and mass that change over time based on fitting formula from stellar evolution to stellar evolution tracks. Neighboring particles that are binaries can actually undergo complicated direct in-body, 3-body, and 4-body encounters. And because we have that in log n scaling, we can really hit high numbers of particles, in this case 10 to the 6, with relative ease. And what I'm going to talk about at the end of the talk today is that we can actually extend that even higher to roughly 10 to the 7. Now, detailed testing has shown that this essentially agrees extremely well with direct in-body. So on the left, I'm showing the results of a comparison to that million-body star cluster simulation that I showed earlier. The Monte Carlo is in white, the direct in-body is in teal. And as you can see, even though there is individual differences between the clusters, particularly for what's called the smallest Lagrange radii, so where the smallest amount of mass is enclosed, overall, the evolution of these, particularly the evolution of the half-mass radius, is matched extremely well between the two approaches. And the nice thing about this is, whereas the in-body methods took about 13 months, the Monte Carlo method took about 2 days to run this exact same simulation. So it really allows us to explore the parameter space of dense star clusters in a way that you can't do with collisional in-body simulations. So what I'm going to do now is show an example of what these sort of parameter space explorations can give us with a particular focus on binary black hole mergers. And then at the end, I'm going to revisit the initial conditions that I talked about earlier. So like I said earlier, roughly speaking, about half of the binary black hole mergers in any given star cluster will merge inside the cluster, as long as the gravitational wave merger timescale is less than the typical encounter timescale. Most of the time, those particles are going to merge before they are ejected from the cluster. Now, whenever that happens, you're essentially left with a new massive black hole. In this case, the mass is roughly, the sum of the 2 component masses that went into it, minus a little bit of tax in terms of gravitational radiation. And if you start off with non-spinning black holes, and in fact, even if you start off with equally spinning black holes, you will typically produce a black hole with a dimensionless Kerr spin of 0.7. And that tends to be true as long as the mass ratios are roughly speaking equal. And so whenever this merger occurs, you're actually given a large, it actually turns out that you experience what's called a recoil kick. So if I have a merger of 2 objects in the cluster, I actually get a massive kick right at the point of merger, in this case, many tens of thousands of kilometers a second. And the reason for that is the following. Imagine I have a binary black hole with significant spins. In this case, each component has a maximally allowed spin of 1, merging with a particular configuration. In this case, imagine the angular momentum is pointing along the z-hat direction, and the 2 spins are pointed at about 45 degrees each, pointing away from each other off of the orbital angular momentum. In that configuration, it turns out the majority of the gravitational waves are going to be emitted in a single direction. And so you can actually get kicks as high as 5,000 kilometers a second from the merger of equal mass binary black holes. Now, for a typical star cluster, like a globular cluster or a superstar cluster, the escape speed is typically anywhere from 10 to 100 kilometers a second. And so any merger that occurs inside the cluster, the merger product is going to be rapidly ejected from the cluster. In fact, for supermassive black holes, the same argument is true even in some nuclear star clusters. Supermassive black hole mergers will sometimes be significantly kicked out of their nuclear star clusters or even their host galaxies at the point of merger, assuming they had extremal spins. On the other hand, let's say I dispense with the spins entirely, and now I have a non-spinning binary black hole. In this case, as long as the masses are roughly comparable, the gravitational wave emission is isotropic about the system, and there is no net momentum gain whenever the merger occurs. In that case, the distribution of escape speeds, which I'm showing over here on the right, is significantly reduced. And something like 50% of binary black hole mergers that occur in clusters actually have recoil kicks lower than their escape speeds. So now, this massive object that I ejected from the cluster will actually stay inside the cluster. Now at this point, few repeated slides there, sorry. Now at this point, I have this massive object in the center of the cluster. It'll sink back there rapidly due to dynamical friction. And because it's the most massive object in the cluster, it will very rapidly find itself another companion and merge again. Now, these are what we call multiple generations of black hole mergers. So in this case, I refer to first generation black holes as those born from the collapse of single stars. Second generation black holes are born from the previous merger of two black holes whose merger product is retained in the cluster. Now, this is what we would typically call a 1G plus 2G binary black hole merger. And in fact, and so one of the things that we obviously wanted to do, and because we can explore these very massive star cluster sizes that direct in-body can't, was look at how often you would actually retain the binary black holes from black hole mergers in the cluster, and then how would that change the detected mass function of binary black holes from the dynamical formation channel. So this is from a paper we put out last year, and what you're looking at is the total mass distribution, so M1 and M2, of every binary black hole merger from clusters taken from a grid of models that was then extrapolated onto a cosmological onto a distribution of star clusters in the local universe. And so you can see clearly that the binary black hole masses from this are much larger than some of what LIGO has seen so far. In this case, you have masses going from 20 solar masses as total mass, so that's 10 plus 10, all the way up to about 120 solar masses at the large end, which is about, in this case, 40 plus 80. So the maximum mass you can get from a star is about 40 solar masses. You merge two of those, and you get an 80 solar mass black hole. If that finds itself another partner, it will create a binary black hole with a total mass of about 120 solar masses. On the left-hand side, I'm showing the actual distribution of mergers in the local universe. The right-hand side is showing the same distribution, but convolved with LIGO's sensitivity function. And so in this case, you can even see some mergers that occur beyond Redshift 1, going all the way up to mergers that are 160 times the mass of the sun. So in that case, that's a 2G plus a 2G merger. For comparison, the current LIGO Virgo catalog looks something like this. I've also shown the total masses from a catalog presented by a group at the Institute for Advanced Study. The interesting thing about this is that you can actually clearly show a distinction between the first generation black hole mergers, whose maximum mass is about 80 solar masses, that's total mass, and the next generation black hole mergers. So the 1G plus 1G mergers pretty much top out at 40 plus 40. The 1G plus 2G mergers top out at 120, and the 2G plus 2G mergers, at least in the detected distribution, can top out at 160 solar masses. Now, of course, if you look at the top of this plot, I've explicitly assumed that the birth spins of all black holes from stars is identically zero. There are some theoretical reasons from massive stellar evolution to believe that this is true. In particular, it looks like some of what we're starting to see is that the coupling between the core and the envelope of a massive star may enable significant angular momentum extraction from the core as the star evolves onto the giant branch, which in turn will spin down the core before its collapse. But this is still extremely theoretical work, and is still very poorly constrained from actual observations. I'm talking about the observations in this case of black hole spins. So to be safe, we want to ask what happens as we dial up the birth spins of black holes. As this happens, it turns out the contributions from second generation mergers decreases until by the time you allow for black holes to have spins of 0.5 at birth, suddenly you've got virtually no population in that really high mass end of above 80 solar masses. And the reason for that is, of course, if I allow spins from first generation if I allow black holes from collapsing stars to have significant spins, the cluster will very rarely retain their merger products and very rarely move on to the second generation. If I ask the same question about this, if I ask the same question in terms of the spin distribution, at the same time, for a birth spin of 0, I typically have a very strong peak from the first generation mergers right at an chi effective spin of 0. And as I dial up the second generation spins are somewhat symmetric about this. So even if I start off every black hole with 0 spin, the repeated mergers of black holes will build up a population of spinning black holes in the cluster. And so even if I assume no black holes start off with spins, dynamics will eventually cause them to spin up through these repeated mergers. Now, as I dial up the birth spins, I retain fewer of those second generation black holes, so the contribution of the wings decreases. But as I do this, eventually the spinning contribution from the first generation black holes starts to take over in terms of the distribution. And so this is actually kind of a neat result from this. Regardless of the birth spins of black holes, dynamics will give you a population of spinning black holes. And the spins will essentially be isotropically distributed on the sphere, which gives you a nice way to sort of detect where some of these systems are actually coming from. Now, people have done a lot of work on this, and in particular, semi-analytic work to try and figure out whether or not you can discriminate first generation and second generation mergers after you've had, in this case, about 100 binary black hole mergers. But one of the obvious questions to ask is there some unique mass? Now, I mentioned earlier that you typically don't see black holes from star clusters, from single stars above about 40 solar masses. And if you look at recent population synthesis, you can actually see that this is taken from a paper by Chris Belczynski, which is that typically speaking, when you consider something called pulsational-pair instability physics, essentially any massive star with a pre-collapse mass above about 40 solar masses is going to completely detonate prior to its collapse to a black hole. And so from these population synthesis studies, essentially you see a sort of maximum total mass of about 80 solar masses. And this has been pretty well confirmed by people like Stan Woosley, who have looked at detailed models of pulsational-pair instability physics. And there aren't really ways to sort of tweak either accretion during binary physics or use hyper-Eddington accretion to significantly get over the pulsational-pair instability gap. There's a paper by Lieke van Soen and Selma de Mink that have looked at this that just came out recently. And so if you can't get above about 80 solar masses from isolated stars, or isolated binaries, that in of itself gives you a way to discriminate these two populations, because this entire area here is essentially excluded for isolated binary evolution. This is what we call the pulsational-pair instability gap. So this is an example of something we can really probe with these Monte Carlo methods that you couldn't accomplish with a traditional in-body integration. Because in order to really explore the production of these multiple generations of black holes, you need to be able to model star clusters with realistic gravitational potentials, realistic escape speeds, and realistic black hole merger physics. And you just can't get up to high enough numbers with direct in-body. Now, having said that, I'm going to revisit now this last assumption I said, and remind everybody that I said somewhat brashly earlier in the talk that there are no dials of free parameters and that the entire thing depends on well-understood gravitational physics. That part is strictly speaking true. But there's a big caveat in this, which is going to become much, much more important as we start to move out into those cosmological distances that I was talking about earlier. Once we start really probing high redshift binary black hole merger events, we're really going to want to understand the formation and evolution of these star clusters better. And so going back to this, I really should put a big asterisk after this first comment. And it really has to do with the fact that there are no dials or free parameters in the evolution of these star clusters, modulo stellar evolution, once you have decided on your initial conditions. Once you have decided that I have a big ball of stars out there in space with a given mass, radius, and initial concentration, then the statement is true. However, this completely ignores the critically important physics of star formation and cluster formation and the environments in which these things actually form. So just to go back and revisit what I mean when I talk about star clusters, globular clusters, which is sort of a good proxy for what we're talking about, all share a few key characteristics. They're all typically very old, 12 to 13 billion years old. They're typically very low metallicity, and at the same time, they're very massive. They're anywhere from about 100,000 to 1 million stars each. But unlike a lot of other clusters out there, and a lot of dwarf galaxies, they tend to be very compact. You'll get stellar densities on the order of 10 to the 5 stars per parsec cubed or something in the center of the most massive globular clusters. These clusters are found in most galaxies. The Milky Way has ballpark about 200. And the number of globular clusters scales pretty proportionally with the mass of your dark matter halo. So M87 has about 13,000 globular clusters. And so if we really want to probe this better, we need to start thinking about where these star clusters come from and the galactic environments that they're created in across cosmic space and time. So the first stab we took at this actually started from a semi-analytic model of globular cluster formation that was essentially taken from halo merger trees. This was a model put together by Kareem El-Badri, who's a grad student at Berkeley. It's a very neat way of treating this problem where you essentially assume that through the process of galaxy assembly, essentially globular clusters will form from gas reservoirs in galaxies, and that during mergers, the process of galaxy assembly will bring these new globular clusters into the assembled galaxies from their parent galaxies. And so by the present day, you end up with a large population of clusters in a single galaxy. They'll typically have random orbits like we see in the Milky Way, and they'll have spreads in metallicity that are dependent on the galaxies that they originally formed in. In this case, the blue clusters, for instance, would be formed in dwarf galaxies many giga-years ago that were then accreted by the Milky Way galaxy. So what we did was we took a bunch of those Monte Carlo models that I was talking about earlier, and we combined this with the cosmological model to essentially estimate the rate of binary black hole mergers in the local universe. In this case, we is actually me and Avi. This is from a paper we wrote a couple of years ago. And the nice thing about this is because we were pinning this to a specific cosmological model, we could make predictions for multiple different formation channels using the same underlying physics. So in this case, we were able to show that as a function of redshift, the binary black hole merger rate increases out to beyond redshift 2 before decreasing after that. At the same time, we were able to add in additional physics. This is taken from using a similar cosmological model from a paper I did with Fabio Antonini, where we looked at the merger rate of black hole triples across cosmic time. And we were also able to add in, of course, the contribution from the field. And so if you add these together, you get a total merger rate, in this case, of about 30 per gigaparsec cube per year. Now, I should point out I cheated a little bit here and actually adjusted the rate from isolated binaries in order to match one of the LIGO rates that was printed in their papers. This was admittedly a bit of a dig at the population synthesis people, since, as I said earlier, the uncertainties in the common envelope can translate to several orders of magnitude difference in the binary black hole population rates. But the nice thing about this is, even though these are vastly different physical mechanisms for creating black hole mergers, it was all done with self-consistent stellar physics and a self-consistent cosmological model in the background. And so that was the sort of first pass at this, just using a semi-analytic model for cosmological formation. But of course, as everyone in this group knows, there are much, much better ways to look at the formation of star clusters and their evolution over cosmic time. And so that brings me to what I'm going to talk about for the final part of the talk, which is something called the Great Balls of Fire Project. This is something that I've been working on with Mike Grudich, Zach Hafen, and Astrid Lamberts, who are members of the Fire Collaboration for several years now. This is all, by the way, preliminary work, so please don't, screenshot this too much. I know it's being recorded, but I reserve the right to change these plots at some point in the future. And so the idea here is that we would take one of these high fidelity MHD models of galaxy assembly, in this case, one of the latte simulations from Wetzel et al., and we would combine it with high resolution models of giant molecular cloud collapse and star cluster formation using the same physics from the fire simulation. This is taken from the thesis, the dissertation work of Mike Grudich, who at the time was a grad student at Caltech, and now a Sierra Fellow at Northwestern University. And then taking the initial conditions from these star cluster simulations, we would then feed this in to the Monte Carlo models that I described earlier, taking essentially our first stab at a fully self-consistent population of dense star clusters across cosmic space and time. And so the way this would work in practice is the following. We would go through one of the fire galaxies, identify groups of particles that look like they're going to form collapsing giant molecular clouds. And when that happens, we essentially use the physics from Mike's we essentially use the statistics from Mike's models of star cluster collapse and fragmentation to figure out what the mass and radius and metallicity of the star cluster are going to be. We can only do this in a statistical sense, but by tracing this through the galaxy evolution, but by looking at each snapshot in the galaxy, we can pin its metallicity to the star formation enrichment history of the universe, and we can figure out what the mass and radius are going to be on a statistical level. Now, we also, of course, have this particle that is traveling through these fire snapshots. So at the same time, we can also compute the orbit itself. And in this case, we can extract a bunch of the relevant information that we would need in order to correctly model this star cluster inside a Monte Carlo simulation. So what I'm showing on the left is a cartoon picture of what this cluster's orbit in the galaxy might look like. On the right, I'm actually showing some of the extracted information for one of the clusters from this catalog that we're putting together. So the top right shows the radius of the particle from the galactic center in kiloparsecs, as well as its instantaneous velocity. The bottom left shows the effective tidal force calculated directly from the tidal tensor experienced by this tracer particle. And on the bottom right, we show the typical dynamical friction timescale. So, of course, the same way that a black hole experiences dynamical friction in its cluster, the cluster experiences dynamical friction inside the galaxy that it lives in. And over the course of its orbit, that dynamical friction is going to drag the cluster into the center of the galaxy the same way that the black hole is dragged into the center of the star cluster. Of course, the difference is once the star cluster reaches the center of the galaxy, it's essentially going to be shredded by the strong tidal forces present in the galactic center. So what we do is we calculate the dynamical friction timescale for these clusters, and after essentially the age of the cluster is greater than the integrated dynamical friction timescale, we assume that the cluster has been destroyed. And so just preliminarily looking at the masses of this, what we did was we extracted all of the GMCs that looked like they were going to form star clusters. And what I'm showing is the masses of about 900 of them, which is the maximum amount I was able to do given computational resources. And so the initial mass of this follows pretty well a 1/m² power law, which is actually really cool. If I then ask, after the dynamical friction amount of integration of these star clusters, how many of them would survive, I'm left with a distribution that looks like this. There are still a reasonably large number of massive clusters, and there's a reasonably large number of, but the amount of low mass clusters has been reduced by roughly an order of magnitude. If I then impose an even further cut and ask, what is the mass of these final clusters at z of 0, then I'm left with this distribution with a fair number of objects between 10 to the 5 and 10 to the 6 solar masses. Plotting on top of this the distribution of Milky Way globular clusters, you can see that we actually, I would say, do reasonably well for things in the mass range of the Milky Way galaxy. We don't quite get the same numbers at the very high mass of 10 to the 6, but I would argue that's actually a sampling effect from this. But there are two big things that stand out from this. The first is this big region right here where we clearly don't agree. And this actually comes from the fact that in order to properly treat to completely treat the tidal evolution of one of these star clusters in a galaxy, we would also need to treat what's called the tidal shocking or tidal heating. Essentially, as the star cluster travels through the galaxy, it experiences a time-dependent gravitational potential. But of course, as we all know, a time-dependent gravitational potential will do work on the star cluster as it travels through this. And so for very big and puffy clusters, you have a lot of radius for the tides to sort of torque on the cluster, and it's essentially inject a lot of energy into the system. And so if I go back to one of these classic papers from Oleg Nedin and Jerry Ostreicher, if you write down an initial population of star clusters just in mass and radius space, the most massive clusters will spiral into the center of their galaxies by dynamical friction. That we treat. The very compact medium range masses, this is on the left-hand side of this plot, will be destroyed by relaxation. Essentially, the two-body processes of the cluster will cause the entire star cluster to diffuse over the tidal boundary within a Hubble time. But the bottom right part of this plot, we're not modeling correctly in CMC. And it's because in order to model the tides, you would actually have to model the 3D potential and its effects on the star cluster, which we don't do in our essentially spherically symmetric code. So that explains this part of it. The other thing, which is not represented in this plot, is that we're essentially forming most of these massive clusters a lot later in terms of redshift than the massive clusters of the Milky Way are formed. The most massive clusters in the simulation actually form at redshifts between 0.8 and ballpark about 1. And we're not entirely sure yet whether that's a particular feature of the physics that we've used or the galaxy that we're looking at, or if that actually has to do with some particular feature of the cluster formation model. Like I said, these are preliminary results. I just wanted to show this because I had talked about, I'd used the title Great Balls of Fire previously and had to sort of pull out of that. So I wanted to at least give people an indication of what we've been working on, and to keep an eye out for sometime in the next few months where we're hopefully going to start publishing the first from this series of papers. In the last 3 or 4 minutes, I'm going to show, though, what a real exploration of this cluster parameter space allows you to do. So if you look at the top right-hand side, or at the right-hand side of this plot, some of these clusters go up to a few or even 5 times 10 to the 6 solar masses. In terms of particle number, that really pushes up to 10 to the 7 numbers of particles. This is well beyond the domain of any n-body code, and frankly, was pretty difficult to do with CMC. Now, the reason this is interesting actually ties back into LIGO. So a couple of weeks ago, LIGO published a new binary black hole merger called GW190412, which had a couple of unique properties. The first was that it has a very low mass ratio, the lowest mass ratio of any binary they've detected so far, anywhere between 3 to 1 and 4 to 1, give or take. And it also has the largest measured spin magnitude for the primary black hole of any system in LIGO's catalog, of LIGO's catalog so far. In this case, the primary had a dimensionless spin before its merger of 0.43. Now, if we go back to this and we look at and so when this came out, I originally hadn't really planned on doing anything with it because, this project is still in prep. There's no real reason to write a binary black hole paper on this while it's still in prep. And actually comparing this to the binary population of this galaxy is something that we're going to be working on in the first series of papers that come out. However, when I went back and looked for for binary black holes whose component masses and primary spin exactly matched GW190412, it turns out I found several events in a single star cluster. Out of 900 star clusters, there was one cluster that was uniquely efficient at producing binary black holes exactly like this. It actually came right from the tail of this distribution, and with a bit of an air of drama about me, I decided to call it Behemoth. And it represents the largest star cluster simulation that we've done with CMC to date, nearly 10 to the 7 initial particles. It comes right from the tail of this distribution. And actually these, the tides and dynamical friction timescale of the galaxy that I was showing earlier were actually computed specifically for this cluster. And in fact, if you look in the top left-hand corner, you can actually see the overall mass of the cluster as it decreases over time. And the 2 slight discontinuities that occur at about cosmic time of 8 and 10.5, or sorry, 8 and about 11, are actually due to spikes in the tidal field that we calculated in the galaxy. Now, in this particular instance, it turns out that the galactic environment didn't play a huge role, just because this cluster was so massive that the tidal field didn't really have a lot to say about it. The dynamical friction timescale, on the other hand, caused the cluster to be destroyed by about redshift of 0.2. Now, I went back and like I said, we identified 3 different systems from this particular cluster model that looked like they were going to form, that looked exactly like GW190412. And unlike the discussion I went through earlier, they were all 1G plus 3G binary black hole mergers. In this case, you have 2 black holes merge, they form a second generation black hole, and that second generation black hole merges again to form a third generation black hole, which then again finds itself another partner and merges again. Now, yes, that sounds vaguely insane. It would require a cluster with a very, very high escape speed in order to retain multiple generations of black hole merges. But Behemoth actually has an extremely large escape speed. It starts off with an escape speed of around 300 kilometers a second, and even over the course of its lifetime, still has a escape speed of about 150 kilometers a second prior to its merger in its galactic center. And so this particular cluster, because it is so freakishly large, produces 1,300 binary black hole mergers over its lifetime. That's over 10 times as much as your typical Milky Way-like star globular cluster. And because of that, it can really probe into these multiple generations of black holes and probe into this much lower mass ratio regime, which is what I show on the bottom right, than a typical globular cluster or a superstar cluster. And so this comes from a paper that we just submitted to AppJ Letters yesterday. It's going to be on the archive in a couple of days, we hope, or possibly on Monday. And what I'm showing here is basically the systems we identified that had properties consistent with the LIGO-Virgo posteriors for GW 190412. The left-hand panel shows the results of searching an entire grid of 150 Milky Way-like star clusters for events that look like this. We found exactly one. And it was just from a purely random chance encounter between two second-generation black holes that by virtue of a very lucky spin alignment managed to be retained in the cluster. On the right-hand side, I show the three candidates that are produced from this single cluster, all of which are formed through the exact same dynamical channel. Two 1G black holes merge, form a 2G black hole. That 2G black hole finds another 1G black hole, merges again. The reason this is so nice is, on the one hand, it gives you the right mass ratio, and on the other hand, it gives you the right spin. If I merge two first-generation black holes, whether or not they have spins, as long as they're equal masses, it turns out most of the time I'm going to get a spin distribution centered around 0.7. The posterior for the primary spin of GW in 190412, though, goes from about, I actually don't remember the lower limit, but the median is about a spin of 0.4, and the upper limit, the upper 90 percentile region, is 0.59. So a 1G plus 2G merger is largely excluded by the LIGO-Virgo gravitational wave posterior. But a 3G merger, it turns out, produces a much wider range of spins. And for a 1G plus 2G merger, where the second generation black hole has a spin of 0.7, it turns out that the lowest recoil kicks you can get from that configuration all happen to give you a final spin of exactly 0.43, right at the median of GW 190412. So the point of this paper, which you can check out in a couple of days, is not to say that GW 190412 specifically came from a dense star cluster, but it's really to point out that if these massive clusters had existed in the Milky Way or other galaxies, then they would be critical to understanding these sort of unique events that LIGO and Virgo are now seeing. We do know that clusters with this mass and concentration exist in nearby galaxies. The Antenna Galaxy, among others. There are superstar clusters that look like they are going to form bound objects with masses of nearly 10 to the 7. So this is not outside the realm of possibility. What is unique is that we are assuming that this distribution of massive clusters produce these binaries in a way that gravitational waves will allow us to probe what we can no longer see in our own galaxy. And so with that, I've gone about 5 minutes over time, which I apologize for. Thank you so much for showing up, especially given the weird format. And I think Avi had something he wanted to say now.
Thank you very
much. Thanks so much, Carlo. It was an excellent talk. Yes, so everyone hold on to your questions for a second. If Avi is here, please go ahead.
Thank you, Carl, for an excellent talk. I just wanted to say to everyone that this is the last colloquium of the spring semester. Spring is all around us, but the semester ended up abruptly, too early, prematurely, unfortunately. Otherwise, we would see Carl in person, which would have been much more pleasant. But at any event, the information we get from the higher administration at Harvard is that the fall semester will take place. It's unclear yet in which format. They still have to decide. It looks most likely that the classes will be given online. However, labs will definitely be opened at some point. The question is whether we will be allowed to resume activities at the ITC. It's not clear yet. The ITC lunch will probably not take place, definitely not in the fall semester, and potentially not in the entire academic year, just because it's a gathering that is a bit risky, not only because a lot of people are gathered in a small space, but also because of the food that we deliver. And we don't want to have a cluster of infections at the ITC as a result. But it still remains to be seen as to which activities will take place and when. And that depends very much on whether there will be a second wave and how the situation will evolve in the coming weeks. Keep watching for any updates on either over email or on the internet in the Harvard Gazette or Harvard Crimson about what may happen. Otherwise, I wanted to wish everyone a productive summer, and we have the privilege as theorists to continue our work. And actually, I found those weeks off to be much more productive because there are fewer distractions. So, I mean, people that do experiments or observations are very much affected by the shutdown, much more than we are. And I encourage everyone to keep interacting with each other, writing papers, collaborating, speaking with anyone on social matters. And let's keep a sense of the community, even in these times of when we don't see each other. And then I very much hope that after the summer, we will be back at the CFA, although it's not guaranteed yet. So have a most pleasant summer, and I hope to see you soon.
Thank you for that.
I actually, may I just ask Carl for a scientific question about his talk, since, I mean, we will start taking questions, and I see already that Selma has a question, but let me just, before I go mute myself, Carl, this one massive cluster that you identified in the simulation, in fact, observationally, Genzel and his group were reporting about very large molecular clouds, they call them, or clumps of gas, they call them clumps of gas in high redshift galaxies at redshift 2. So it's quite possible that objects like that are much more common at redshift 1 or 2 than they are today. And it's just that your simulations are not showing them to be so common. It's not fully understood where the clumps that Genzel identifies in those high redshift galaxies come from and what they mean.
Yeah, I mean, there's the field of sort of cluster formation is just sort of the Wild West, and I am not an expert in it, despite starting to poke my nose into it. The impression I get is that, so the old papers by Gnedin and Ostreicher, the claim they made was that even if star clusters formed according to a 1/m² power law, which is consistent at least with some observations in the local universe, the most massive clusters would rapidly spiral into their center before the present day, eliminating them from what we would observe, for instance, in the Milky Way globular cluster system. However, there is a lot of debate whether or not the 1/m² is actually what you would see in realistic situations, or whether or not there is some sort of Schechter-like truncation that comes from the galactic environment itself. I am unfortunately not the person to ask about that. That gets into the real complicated part of sort of hydrodynamics and hydrodynamic shearing that I'm much less of an expert in.
Thank you. Selma has a question. Go ahead, Selma.
I hope my microphone is unmuted. I'm doing this from my phone the first time. Thanks, Carl. I really enjoyed that. I've seen parts of it many times, but very nice to see all the new results. I have a question about the new event, the mass ratio 0.3 event that I think you touched on in the very last slides of your talk. Can you comment on can you comment on how common you would find these events? Maybe I wasn't paying full attention, but it is event number 11 that is reported now. We had a discussion with Frank Oma in a seminar series between Fermilab and some other place. He commented that the rate of this would be of the ballpark of 1 out of 10, 1 out of 15. I guess that's too early to say, but would you produce high mass ratio events at such high rates?
Well, so first of all, I disagree that the effective rate would be 1 out of 10, because keep in mind we have an LVC bias here, which is that they published this after their observation of 50 or so binary black hole mergers. This is just one of the ones they thought was interesting enough to publish before the catalog.
I was not quoting my own opinion, but Frank Omu is one of the members there. So
yeah. Fair enough.
Yeah.
So this particular channel is relatively rare, obviously. In terms of low mass ratio events, that we can actually seem to do relatively well. So I'm showing the mass ratios here, and basically everything, and basically roughly about 8 to 9% of all mergers from star clusters, and particularly from this massive cluster, tend to be below mass ratio of about 0.4. So consistent with the LIGO-Virgo posterior distribution. In terms of the absolute rates, it gets a little tricky because what I did in particular was identify things that look not only like the masses of this object, but look like the spin of it as well, the spin of the primary. And that, unfortunately, is hard for 2 reasons. One, I'm binning this according to the LIGO-Virgo posteriors, and so that's not really a good way to put together any sort of rate estimate. The second one is obviously just small numbers. We have one massive star cluster that produced 3 of these objects. And while that in of itself is intriguing, at least intriguing enough for me to write an AppJ letter about it, I would not want to hazard a guess at to the rates out of it. Now in the paper, I did a sort of back of the envelope estimate where I was like, let's assume every Milky Way formed in one cluster like Behemoth, that it was destroyed before the present day. In that case, roughly 1 out of every 100 events would look something like this. However, in the paper, I then go on in the next paragraph to immediately trash that back of the envelope argument as being unrealistic and depending on and sort of benefiting from small number statistics.
Thanks.
Laika? And then I have a question after that.
Sorry, yeah, thanks, Carl. Cool talk, indeed. I also want to ask something about the GW 190412, but more on the spin side of it. So I think you still assume a 0 birth spin for all black hole mergers in this huge cluster, right? Mm-hmm. But if you would rank them up a little bit to have low birth spins, I don't assume they would escape immediately because it's such a huge cluster. But what would it do to the spin argument? Like, would you get the same spins if you combine the 2nd generation 0.7 spinning black hole with a low spinning 1st generation spin black hole? Would it create the same spins, or would it get to different mismatching maybe?
So it's kind of a problem there because, so the problem is if I merge 2 roughly equal mass black holes, whether or not the black holes are spinning, I will typically produce a distribution of remnant spins that is peaked around 0.7. That part is hard to get around, and that in particular is excluded by the LIGO-Virgo posterior. If, on the other hand, I have a 2-to-1 mass ratio and just one object, actually, I'm going to pull up real quick the paper itself because there's a plot in there that I did not put. This is one advantage of doing this over Zoom. There's a plot in there that I did not put in the talk that I think makes this a lot clearer. Okay, so can everybody see this plot right here?
There's a paper in front of it.
There's a paper in front of it?
Oh, no, now I see it. I think there's just a lag.
Right. So what you're looking at here is, this is just a semi-analytic calculation where I basically combined a bunch of 1G and 2G black holes and 2G and 2G black holes. And the x-axis is showing the final spin that you get out of this. Now, you get a wide distribution depending on the orientation of the spins of the progenitor black holes. But in both cases, if I don't take into account the kicks of the objects, they're essentially peaked exactly at, in this case, 0.67 for 2G plus 2G mergers, and 0.62 for 1G plus 2G mergers. The difference there comes from the mass ratio. However, it turns out that the recoil kick of the black hole and the final spin that the merger produces are correlated in such a way that if I limit myself to those black holes that get kicks below 100 kilometers a second, pretty much everything that's a merger from a 1G plus 2G black hole lies within the LIGO Virgo posterior. The same is not true for the 2G plus 2G merger channel, which is what you would see if you started off with black holes with significant spin. You can see it even more clearly here. Here I'm comparing the recoil kicks to the final spins directly. And in this case, the lowest recoil kick systems, that all of which lie within the, the systems with the lowest final spins, all of which lie within the LIGO Virgo posterior, all happen to have low recoil kicks that are originating from 1G plus 2G mergers.
Okay.
So
thanks.
Yeah, part of it's a selection bias that your cluster escape speed makes it more likely to retain a certain spin configuration or a certain remnant spins than others.
We say we take another question from David, who has his hand raised.
Hey, sure. Hi, Carl. I really liked the talk. Just wondering, so the code you're using, the Fokker-Planck code, is it true that I guess it assumes spherical symmetry, right?
Yes.
So obviously, like you said, you were talking about the initial conditions before, and these clusters are subject to tidal forces. So I'm wondering that, you know, the spherical symmetry issue, if that might become a problem, or if it's any problem that one should think about that assumption.
That is actually a big part of our issue in implementing the tidal forces. Because, I mean, essentially, we've reproduced the issues with we've reproduced the same issues that the binary stellar evolution people run into when they want to handle an eccentric Roche-Loeb overflow system. Because now we have some system that is rotating with respect to its host galaxy on a highly elliptical orbit, and is experiencing Coriolis forces, centrifugal forces, Eulerian forces, assuming you're in the cluster rest frame. And so you end up with this problem where essentially you want to treat all of this complicated dynamics that depends on the 3D velocities and positions of each particle in its 3D cluster with a 1D code that only tracks tangential and radial velocity. So essentially what we do is we just assume, we calculate what the effective tidal boundary would be, assuming a circular orbit based on the tidal tensor. It's a limiting assumption, but for now it's the best we can do. To actually to do somewhat better than that, there are approximate ways I've been looking into where we could include tidal forces in an orbit averaged sense that's actually consistent with the Fokker-Planck approximation. If we wanted to dispense with spherical symmetry, though, then things become a lot more difficult. You have to deal with the diffusion coefficients that also take into account angular momentum, but you also have to find some way to calculate nearest neighbor particles and some way to calculate this overall structure of the cluster. It's a significant problem that I've frankly been scared to actually try.
Sure. Thank you.
Okay, we're pretty far over time, but if you allow me, I just wanted to ask one more question, Carl. I was curious, when you're talking about your Great Balls of Fire project, you mentioned that the clusters, right when they get too close to the center of the galaxy, can be disrupted. Mm-hmm. And so, you know, Liouville's theorem might lead you to believe that perhaps when you're disrupting these clusters, you could still have a high number of black hole interactions, binary black hole interactions. Are you looking at the clusters once they've disrupted? Do you expect mergers even during, or interesting interactions even during the disruption, or does it just happen too quickly? What do you do with these disrupted clusters?
We delete it from the simulation just because there's no, or we don't delete it, sorry, but we consider that the final time of the cluster and we say, all right, it's done. I think there's a lot of really cool physics you could do with that aspect of it, because you could, for instance, track what kind of populations are being deposited into the galactic center. How do you build up a nuclear star cluster? How long does mass segregation take within that nuclear star cluster that you've just constructed. That is a very cool project that is unfortunately well beyond the capabilities of CMC. That's on my very far in the future to-do list.
Yeah, that sounds interesting. All right, thanks so much again. See everybody around.
Cool. Thanks, everybody.